Hello students, this is Mr. Allen. Today we are going to look at section 1.6. That is limits at infinity. I'm going to do a better job today of making sure we keep this at 10 minutes or less. Our objective today is to determine finite limits at infinity, determine the horizontal asymptotes, if any, that a graph of a function has, and to determine infinite limits at infinity. So this section discusses the end behavior of a function on a finite or infinite interval. So consider the function f of x equals 3x squared over x squared plus 1. So here's the graph, as you can see here. Now notice that we can only really see in this graph from negative for x equals -4 to 4, but we notice that as this graph continues, if it continues the same trend, as x goes to infinity, it appears that the y value, f of x, is going to 3. And as x goes to negative infinity, it appears also that f of x is going to 3. So this is exactly what we're going to be looking at. We're going to be considering what's going on when we take the limit of a function to infinity. In this case, we're going to say that it's 3. What is that? Graphically, you can see the values of f of x approach 3 as x increases without bound or decreases without bound. We could also use the numeric method. So if we look at a table here, now notice our x values. So I've used x values of 0, 1, 10, 100, infinity. But notice what's happening to the y values. Well, they're getting bigger, but they're going 2.97, 2.9997, and then as the x value is getting bigger, it's getting closer to 3. It is approaching 3. The table suggests that the value of f of x approaches 3 as x increases without bound, and that is exactly the limit. Similarly, f of x approaches 3 as x decreases without bound. So that would be written in this way. So the limit of f of x as x goes to negative infinity is 3. And we also already saw that the limit of f of x as x goes to infinity is positive 3. These are known as limits at infinity. These are not infinite limits. The limit is a finite value of 3. But we are looking at the limit as x goes to infinity. To say that a statement is true as x increases without bound means that for some large real number m, the statement is true for all x. Now, we could get into the epsilon delta definition of limit here, but I'm actually going to go ahead and skip that as that was an optional section or an optional concept. So, horizontal asymptotes. So in our last example, we saw that as the limit went to infinity, the f of x values were going to 3. If we think about it this way, if we've got, this is a different function, but so we've got our x-axis here, we've got our y-axis here, we've got some function that does some interesting things, and as it gets closer and closer to x going to infinity, what we're hoping is that this little squiggly thing here is going to calm down, and we're going to hope that it straightens out. And so let's just go back to that 3 that we used in the last example. So we might say that the limit of this function as x goes to infinity is 3. Well, this is precisely how we're going to define a horizontal asymptote. The line y equals L is called a horizontal asymptote of the graph of f. And then here's our definition. This is important. The line y equals L is a horizontal asymptote of the graph of f when the limit of f of x as x goes to negative infinity equals L, or if the limit of f of x as x goes to positive infinity is equal to L. Note that from this definition, the graph of a function of x can have at most 2 horizontal asymptotes, one on the left and one on the right. And there are examples that we might look at. We'll see. I'm not sure if we'll get to all of them, but there are examples of graphs of functions that have 2 horizontal asymptotes. Limits at infinity have the same properties of the limits that we've discussed thus far. Now, I want to make sure that this is clear. This is the definition of a horizontal asymptote. So in the future, if I ask you a question on a quiz or a test or a homework assignment about horizontal asymptotes, this is the definition that you need to be looking at. Here are a couple helpful limits at infinity rules. So I'm just going to look at the first one, and actually, I probably should look at both of these. Let's look at this example right here. So let's say you have the limit of a c over x to the r. C could be a constant. So let's just say 7 over x to the third. What's the limit of that as x goes to infinity? Well, hopefully you remember from one of our earlier lessons, anytime you take a constant divided by a infinity number, so you're taking infinity to the third in this case, essentially, if you did a direct substitution, this is going to be 0. The nice thing about this theorem is you don't have to go through that analysis. You can just refer to the rule. You'll also notice that this is also true if x is going to negative infinity. Now, remember the graph of e to the x? So I'm telling you, if you go to negative infinity, if x goes to negative infinity, e to the x is going to go to 0. Remember, the graph of e to the x looks something like this. If you do the limit of e to the negative x as x goes to infinity, that is also 0. So here are two examples. So example A says, what is the limit of x goes to infinity of 5 minus 2 over x squared? Well, we can use our properties and say, well, that's going to be the limit as x goes to infinity of 5 minus the limit of 2 over x squared, again, as x goes to infinity. The first limit is 5. That's one of our rules. The limit of a constant function is the constant itself. This is by the last theorem we just looked at, which I believe was theorem 1.6. So this is 0. So this limit is 5. This limit is 5. So what does that tell us about the function y equals 5 minus 2 over x squared in terms of horizontal asymptotes? So let's go ahead and look at the next one. The next function here is 3 over e to the x. Again, we're looking for the limit as x goes to infinity. So again, we could use our rules. And actually, let's do an algebra rule here first. We could say that this is the limit as x goes to infinity of 3 times the limit as x goes to infinity. I'm going to do a little trick here. This e to the x is in the denominator, so I can move it up to the numerator. So then this limit here is going to be, well, it's going to be 3. The limit of 3 as x goes to infinity is 3 times, and then based on our theorem that we just looked at, we learned that this is 0. So this limit is 0. This limit is 0. Okay, horizontal asymptotes. Here are some guidelines for finding limits at plus or minus infinity of rational functions. If the degree of the numerator is less than the degree of the denominator, then the limit of that rational function is 0. We just saw an example of that. If the degree of the numerator is equal to the degree of the denominator, then the limit of the rational function is the ratio of the leading coefficients. So what I'm saying here is if I did a limit as x goes to infinity of, let's say, 7x to the third divided by, let's say 8x to the third minus 7x, you just look at the leading coefficients. Since these have the same degree of x to the third, so the answer here would be 7/8. And then the third one, if the degree of the numerator is greater than the degree of the denominator, then it's D and E. It's D and E. This is a very helpful these are very helpful guidelines. I highly encourage you to spend some time studying those. Okay, horizontal asymptote. This curve here, the graph of this function is here. This is known as the Witch of Agnesi. And we can just simply use the guidelines we just had here. The degree of the numerator is 0. The degree of the denominator is 2. That means the degree of the denominator is greater than the degree of the numerator. Therefore, this limit as x goes to infinity of f of x is 0. And we have that written down here. In other words, it also applies when we do the limit as x goes to negative infinity. Both cases, it goes to 0. So guess what we call this right here? Guess what we call the line y equals 0? It is a horizontal asymptote. All right, we're almost out of time here, so I know we're right at 10 minutes, but I need to hit two more things here real quick. This one here is, I just want to make a note. A vertical asymptote, by definition, is when the limit of a function as x goes to a constant, in this case, I'm going to call it 1 over x. What is the limit of this? Well, that's d and e when x goes to 0. Hopefully you remember the graph. I'm actually not going to review that with you now. You should know. We've talked about it in class. This gives us a, and actually here I could put it this way, slash infinity. This gives us a vertical asymptote. However, if I do the limit of the same function as x goes to infinity of 1 over x, I get 0. That is a horizontal asymptote. So what I'm trying to tell you is this. We define a vertical asymptote as a limit going to a constant being infinity. And we talk about a horizontal asymptote as the limit of a function going to infinity as being a constant. So you just got to switch the two around. That's how we define vertical and horizontal limits. Last but not least is limits, infinite limits at infinity. I'm not actually going to go through and read this whole table to you, but it kind of makes sense. There are some functions that are going to grow without bound as x goes to infinity. So let's just look at an example here real quick. So what if I wanted to find the limit of this? Well, let's see here. We're going to do as x increases without bound. So we're going x is going to go without bound. What is going to happen to x to the third? Well, it's going to grow without bound 2, so we would say the limit as x goes to infinity of x to the third is also infinity. Now that helps us understand the end behavior of this function. But notice this is not going to give us a horizontal asymptote because this is not a constant. We could also say the same thing about the second version of this, which is when x goes to negative infinity. So this is going to be the limit as x goes to negative infinity. Infinity of x to the third. What's that going to give us? Well, it turns out that it's negative infinity. Okay, so again, this tells us a little bit about the end behavior. I think I've got the graph on here, which might get in the way. Oh, it's on the next slide. Good. So the end behavior of this function is it's tending towards infinity as x goes to infinity. And this one's tending to negative infinity as x goes to negative infinity. Okay, so I didn't keep my promise here. I apologize. I did not keep it under 10 minutes. Sorry.